Alrighty, welcome back. We're here for another episode. Today I'm joined by Associate Professor here at the University of Houston in our Physical Chemistry Department, Professor Jerry Yang, who grew up in Taiwan. And so I'm really excited to have him on today because I think you were actually one of the first P chemists I've had on. So I'm really unfamiliar with, well, to be fair, I'm really unfamiliar with the work you even do here at Houston. So I'm really excited to talk with you today and get a glimpse into in PChem. But before we get there, like I mentioned, I mentioned you grew up in Taiwan, so perhaps we can start there a little bit, learn a little bit about yourself for the audience, and we'll kind of grow into this podcast a little bit. But I know you did your undergraduate degree at National Taiwan University. Are you from? Are you kind of from the Taipei area, or did you grow up?
Yeah, I grew up in a Taipei city, so actually that's the capital of Taiwan. And since I was born, I would pretty much live the same in actually the apartment for the whole time until my college years. Even the master program, I pretty much lived the same place. Although, of course, when I was a kid, we kind of have a 6-member family, so including my grandma on the father's side, and also my eldest aunt. So kind of lived together with also my parents and me and my younger brother. So and then later on only when we have entered college, and then my parent they had another apartment above the floor, so we have a bit of our room. So before that, basically we all live in a quite a small
Yeah,
apartment.
I've noticed that with a lot of even European, but I feel like it's only really in America. It's like a lot of extended family would all live in the same
Sure.
household. Pretty much. I mean,
Right.
European and Asian communities, it's not uncommon at all for an
Right,
entire
right.
family to live in the same household. But in America, I grew up. I live with my mom and dad, but none of my extended family, and so it's kind of interesting. Um, I'm actually kind of a privilege, really, to be, living with extended family and having that sort of environment. It's really cool.
Yeah.
Now in Taiwan, we were discussing. I guess we were shooting emails back and forth, and I mentioned that saw that you were in the chemistry Olympiad, and so I was kind of curious, were you always in the chemistry at a young age, or how did that kind of all transpire?
Not actually. So I can tell you a little bit about what I how I grew up. In fact, the favorite subject, my favorite subject was math. Okay, even till today. No,
I was gonna say it's
for
not all
example,
surprising. All right, yeah, math and PChem,
yeah,
not really all
if I
that's.
see something like a YouTuber or something and say, okay, solve this math Olympia questions, and then I will stop, and I'll even spend time to solve it myself, and then see, okay, if I can get it quickly. Actually, I'll see, okay, how that is solved on the YouTube. So in fact, I have natural, you could say, drawn to math. So my elementary years in math actually is something I really love to do. And then during the junior high, we have this thing. I don't know. It seems that in America, this kind of mathematics education is not really preferred one because I look at my kids, my 2 daughters, their math education. It seems not as the level kind of abstract or that kind of mathematical proof that we learned, when I was in the junior high years.
Mm.
And but at that time, of course, I know my classmates, some quite many classmates, they suffer.
Mm.
Okay, because that kind of, you can say, logical kind of steps, a connection from one step to another, to really think about how you can really mathematically, logically prove a statement. That thing I enjoy a lot. Okay, but
Yeah.
I know my classmates, they suffered. so
Have you
so that's kind of thing I was naturally drawn to.
just on that
So in
just on that real quick because
actually,
I've only ever been in America, so I've only received education from the American school system. But anything kind of in particular stick out that's been even when you were growing up through junior high learning math versus as you mentioned your daughters now, anything kind of stick out that's just different, specifically or
uh, Yeah, I say quite significantly different. But I think also there's also quite a bit of a discussion about what kind of math the kids
Mm,
education should be, because if they learn a lot of those kind of abstract things, maybe it's not really meant for them, for most
mm,
of them. So I can see that also now the education system try to really, you can say, change in a way more practical, and that's kind of what I see in
mm.
education here. It's more try to
Okay.
make it more like relevant to your life experiences, and then try not to make it so abstract that it kind of make a student feel disconnect. And of
Hmm.
course, in America, there's also all kinds of the consideration for the equity or backgrounds or socioeconomical, those kind of issues that intertwine together. So I said that there's quite a bit of consideration for the system in America to do it doing this way. I think
Yeah.
it applies to all the STEMs, I think,
Mm.
fields.
Yeah, I hear you there. So math was your favorite subject growing up.
Yeah, right. So yeah, so junior high the math, and also in a senior high also math. But of course, I like sciences. Okay,
Yeah,
the
sure.
uh, physics, chemistry, basically, I like them. It's just that okay. Backtrack a little bit. In Taiwan, we have this entrance exam. So even from elementary school, basically from first grade to sixth grade, and afterwards also first grade to sixth grade, and then sixth grade to seventh grade to ninth grade. This we call it junior high school,
Hmm.
and there's entrance exam from the ninth grade to the 10th grade, and then you, depending on your exam result, and you get selected to enrolled in different senior high schools.
Hmm.
So I got exempted, okay, because some kind of path. You say, basically say that gifted, or maybe here like Vanguard kind of thing.
Yeah.
But I took a separate exams, not the usual like entrance exam for everybody. So I got lucky. I got enrolled in a gifted class in my senior high school, and there in that class, basically everybody's smart. Okay, so we have even those smart uh, friend who is so smart that math question, those tough chemistry or that math Olympia question for him is like something that he later, in fact, that year that he went to international math Olympiad, you have 6 questions or 8, I forgot. He got
Hmm.
all of them correct.
Oh Jesus.
Full point. Yeah, so that's so smart. For me, from the same school, you can only have limited number to get selected. So
Sure.
only at that time, okay, probably the path forward is not going to be very smooth. So let me think about another subject. And then during that time, Taiwan started to have the you can say the representations in chemistry Olympia.
Yeah.
So that's math. That's for a few years, and then chemistry that's for the second year we have the opportunity. So I said, all right, now math probably would not work out. I said, let me choose chemistry because chemistry actually was my second favorite subject. So, so that
That's really
was
cool.
the thing. Yeah.
Well, I noticed like in your CV though, it said like you had won like a medal in Italy. So you guys, I guess you had
Yeah,
traveled
right.
to
That
Italy.
year was in
How was that?
Italy.
Like,
Yeah.
how was that experience? Like, what did you? Because that's a really cool experience.
That that
I
yeah
mean,
that was great. That was great. Yeah.
how'd that all transpire? Like, what
Um,
happened there?
well, in fact, that we have a little bit of kind of story. Even it's quite a kind of a lot of stories leading up to the experience in the international competition. So of course we have to go through the school level, and then
Hmm.
go to the city level, and then also go to the province level, and then eventually you get selected in a special selection committee, and then represent. It's something like here in America we have this. I'm basically the coordinator for the Greater Houston section. So
Okay.
in America, what we have is that we have the high school students. They can be enrolled in the local competition by their teachers. There's no limit, so it's basically simpler
Hmm.
compared to what we had in Taiwan. And then everybody can try. and of course, the different regions they have those kind of slots.
Mhm.
So last year we have 12 slots, but because of the various additional rules, we got 14 students who can represent the Greater Houston to participate in the national competition.
Oh wow. Okay.
And then national competition, then you have a top 20 being selected into so-called study camp.
Okay.
And then when you have study camp, then the last four, they would choose 4 plus 2 as a backup, so as the representative for a nation. Okay, so that process basically had multiple stages.
Mhm.
So when I participated in Taiwan, what I have is that basically I made the decision to participate in the chemistry much later, because more like figure out, okay, math probably not going to work, not going to have a chance, so let me try chemistry. So basically I use whatever I learned in the chemistry course and had to participate. And then in the school level, I was not even ranked that high to be going into a city. So, but because those people kind of ranked in the front, maybe they have their other thoughts. Maybe they want to focus more on the like a medical. It's a different medical system, so
Sure.
a school system. So they do medical system and enter it right after high school. Not like
Mhm.
here after college you have med school. So there they want to focus on going to med school. So in that case, then they don't want to be distracted. So those like a front runner, they gave us their slot. So I kind of enter the city competition there. And city I did well, but province I did really bad because I kind of late comer, so not really knowing what to anticipate. So in a way, going into the international ones, I did not really know how I got in. I got selected. Maybe the selection committee saw my potential or something, but I thought that basically I would be the no, just had the experience, not
Yeah.
having the opportunity.
Just along
And
for the ride.
having yeah. So international one also okay. So that's a good thing. International competitions, also the national competitions here in America, basically they model the format. So they have the practical side, particle part, that's experiments. Usually the experiment you are contain parts that related to analytical chemistry, like titration. Okay,
Mhm.
that's one part I typically like that. There's another part that typically will involve the organic chemistry, organic experiment. So, and then you also have the theoretical part. That's the written part of the exam. So in the international competition in Italy, we have the practical part. Usually the practical part happened first, and then you have the theoretical and written
Mhm.
form of the exam. I remember that year I I basically screwed up in my organic synthesis. I remember it was some kind of oxidation reaction, and then the instruction tell you to add maybe one equivalent of the reagent, something like that.
Yeah.
But I did not have those kind of a lot of experiences on those kind of thing during high school. So latecomer, not have much practice. So I basically second guess myself. I said, is that enough? I too much, and then you know what happened? It's over oxidized. Okay, it become. I think you want to get it to the aldehyde, and then if you keep going, it become carboxylic acid,
Yeah,
something like
yeah.
that. Okay, and then I think I screwed up totally that. So that basically, you were so depressed. I said, okay, I screwed up. But then that happened. The written test came up later. I said, all right, just like the mentality I had before, is that okay, I'm given the opportunity. I'm not. I'm basically, as you can say, the black horse or something in that
The
sense,
dark horse,
not
yeah.
being really
The underdog.
anticipated. Yeah, dark horse. Yeah. So I said, all right, just give it a try. Give my best shot. It turns out that the written part I did well enough to make up for the part I lost in
That's
the
crazy.
government. So in a way, I kind of get an experience. I always have this idea that yeah, you may feel discouraged because of the situation. You did poor, but yeah, look on the bright side.
Yeah, I mean,
And then do your best.
what a just great experience, and like to be able to have that, especially like a young age. Um, I
Yeah,
mean, you're traveling and like you mentioned, I mean, you were kind of there just for the, the great vibes, and you were just happy to be there, and it's, and you just happened to win, so that's really awesome. That's really cool.
yeah, yeah.
Um,
I was very, very thankful for that experience. Yeah,
and so I
and of
assume
course,
then
that kind of is a life changing
for sure,
or
and then
major experience.
I assume then this kind of like put you on the trajectory towards. I mean, I'm sure some of it to where you are now for sure, but um, this Olympiad experience, did it help you kind of decide that you definitely wanted to pursue like chemistry at the National Taiwan
In
University, or?
fact, that so during the senior high school to the college again in Taiwan, you have this entrance exam.
Mm-hmm.
I also go the different route. Just try to go for those basic sciences. So they have also different way to get the entrance, not to basically exempt the entrance exam. So I got that exempt again, but I participated in math. So in fact, before going to the college, I actually have two majors I could be enrolled in. One is math and one is chemistry. Okay, because of the international competition experience. So the professors that who you can say supervised us or helped us along the way basically talked to me and said that, oh, you should enroll in chemistry. Okay, don't do math. No, do enroll in chemistry. And they kind of tried to persuade me to switch. And then they even used the tactic saying that, oh, you can enroll in a chemistry major, and then you can take math as your second major, or no, so you'll be okay. While the reality is that those majors they have very like a heavy course load, right?
They
So you
do.
are not able
No overlap.
put all the
Yeah.
courses into 4 years. So ultimately, I only have like a chemistry major and a minor in math. I think only like one or two courses short to get
That's a
that done.
shame.
But
Universities know the new
unfortunately,
universities, they know what they're doing too. Like they know damn well they could help you out. They could just like, give you two extra courses and get that major, but oh well. You get the minor
so in
though.
a way, it's more like the professors, kind of talked to me, persuaded me, and said, "Well, then chemistry also is good, and then chemistry also utilize math." And in fact, that also linked to how I chose a physical chemistry.
Mm-hmm.
In fact, it's not physical chemistry. I chose it. I was not really I chose it on my side. I was more like a guided, okay, by the professor. I asked. It actually is a he is a organic professor.
Mm-hmm.
So in the chemistry Olympiad, they basically will require the student to have knowledge until their sophomore year.
Okay.
So you're in chemistry sophomore year, the education, you have organic chemistry, right?
Yeah.
You have a Gen Chem in your freshman year and organic chemistry in the sophomore year. So naturally, you know more of organic chemistry. In fact, I learned organic chemistry myself. Tried
Yeah.
to read in high school, doing read the textbook, and then try to gain that. So in a way, you're more familiar with organic chemistry.
Yeah.
So in terms of like research, they will say, okay, naturally, I went asking organic chemist and see if I can join his lab.
Mm-hmm.
And he told me, I said, oh, you're also good in math. Don't do organic chemistry. So basically, he didn't want to take me because I was good at math. So he pushed me
He was
to
helping you out.
a chemistry colleague he had. And so I said, all right, I got pushed away. So in fact, I was pushed away.
Did you feel
And
upset at all,
then
or is it kind of, I mean, obviously it turned out good, but like in the moment where you're like, oh wow, okay.
well, I was more like
I'm
I
kind of
don't know much
relieved.
to anticipate. I
Okay.
because my family, my parents, they don't really know what is research, right?
Yeah.
So
Yeah.
yeah, so that I grew up in the background. I don't really know much of research. In fact, I didn't even know what I wanted to do. So
Yeah.
when I was in have a math major opportunity enrollment, I even think, okay, I don't know what to do. I don't know the future career. But maybe just join the math department. And math can do multiple things, right? You can do
Yeah.
statistics. You can do other things. So kind of delay. It's a delay tactic. So you delay your decision to a later kind of way. So in fact, I was like, okay, organic chemist is not taking me. All right, let's move on. Just the suggested, of course, the suggested PChem faculty is also well known, and then it's a well respected scholar. So I asked, and then he actually suggests me to join newly hired young faculty. Yeah, PChem faculty, theoretician. Okay, so that's how I ended up joining a theory group,
Oh
theoretical
boy.
study group for my bachelor kind of learning and later become my master degree. So in a way, it's not by design or by
Yeah.
my active choice, but
D-
yeah, it worked.
During your time there, what were you like? What were you kind of looking at as a theoretical chemist as an undergraduate?
Yeah, theory. Yeah, I like math though, so that is not a really you can say something scary, too scary for me. So
But I mean, like, what were you like?
of course,
Were you doing like undergraduate research?
yeah, but during that time, of course, I have also all kinds of other courses.
Sure.
Like also physics major, those kind of courses. So that took quite a bit of time. So in a way, undergrad research is more like learning. Yeah, learning
Okay.
the theoretical tools that we can use, or also the the kind of things related to theoretical research,
Yeah.
not the computation. Not like you use package to compute to compute. No,
Mm.
it's actually you form a theoretical model and try to model things. So that's the thing. So in the master program, that's what I used or did for like a conducting molecularly doped. So for example, carbon 60. Okay, molecularly doped like a conducting polymer. Okay, so
Okay.
that's kind of a thing. I try to see how charge transfer between a conducting polymer with a molecular a donor or acceptor, and see how the charge transfer rate or mechanism or the structural deformation, those kind of effects.
Mm. That's really cool. Now, I know. What I'm curious to pick your brain about is like after your master's degree, you went to go and do a PhD at I think it's CalTech, right? I think it was CalTech with Professor
Yeah, yeah.
Ahmed Zewail, who went on to win a Nobel Prize. But before we get there, what I'm curious is like, I mean, at what point did you like want to go do a graduate degree? Well, I guess you already had a master's degree, but I mean, I guess go pursue the PhD and like also in addition to that, you know, I'm sure leaving Taiwan to go to California was definitely not an easy decision,
Yeah.
right? So how did that kind of work with your family? How did they take that you really wanted to go do this?
I think my parents. Of course I'm very thankful for their being very open minded, and then see whatever is best for me. Then they will just just say, um, let me go ahead, and then and encourage me. So they already had kind of heard from the professors during the time that of course they have some kind of side communications, so they kind of anticipated things later on. In fact, the faculty members talked to me and said, "Well, you should just go straight, go ahead. No, we have a mandatory military service in Taiwan.
Mm,
So and just say after your college degree, go to the military service and then quickly go out. No, so that's kind of their uh, encouragement, and in a way, it kind of feel basically because of the environment, because of they also do active research, so that's kind of anticipated. But I was debating whether I really wanted to go right away or maybe do at a later time. Yeah. So eventually, I decided to do a little bit later, and during that time, I also was participating in some kind of other things that is also kind of related to the you can say related to faith. In fact, that's a lot of stories. during the time when I was young, of course, you academically performing well.
Mm-hmm.
Then everybody would think, oh, you are naturally on this certain path. You can do well in the future. That's kind of the Asian mentality. You
Yeah.
say, okay, if you can do well academically, the future is bright. But I have questions about my own life. Because you ask yourself, okay, you can do well in classes, but what's the purpose? No,
Yeah.
is that the way to happiness? No, and then that's the way that you seek a meaning. So in fact, I ask myself the question, so I don't really know. Okay, so during the college years, I started to kind of meditating on these things and also have the opportunity to explore. So ended up okay, having this acquired faith, and then that I also see that science and faith actually they are really in harmony, not in any conflict. Okay, but while people would think that they are in conflict. So I feel that I would like to have more chance to develop that before I set out to be on my own and then kind of fully immerse in the research. So in a way, that's kind of it can dual purpose for having a master program, also participate more in the church, and then also something like can say community kind of work kind of thing, and then afterwards then come out to for the PhD program. At that time, it's more like okay, it's probably time kind of
Yeah.
feeling. Yeah.
That's really cool. I should say it's very insightful. I think that you mentioned that because, as we've been discussing, obviously, like you're always, always performing well academically, whether it was math or chemistry. Obviously, the whole Olympiad experience. So I feel, were you always kind of struggling with, why am I kind of doing this in a sense, like even all the way through up until your master's degree? Because I feel like you're just kind of, I mean, you really are in some cases, like you really are on like these train tracks to like projecting because you're doing well academically, but maybe were you always struggling with, do I really want to do this? Or because of like
in fact, yes, I did.
Yeah.
That basically, it seems for me that I'm on the track that everybody is anticipating.
Yeah.
Okay, we're kind of thinking that's like a very logical and a reasonable path, but I don't know for myself, and then I don't know if that's the meaning for me.
Yeah.
So a lot of times, you want to solve those kind of life relevant questions first, and then later you have like less bumps along the way.
Yeah.
Because it could be that you go on some path but not figuring out those fundamentals, and then only along the way you find out, oh, this probably is not the path, and you start questioning a lot of things, and then that become I would say a much difficult situation. So I'm really thankful for the time, even though it's probably not as early as some of the typical like PhD students. Yeah.
During that time, what were some of the things that kind of helped you, let's say, like come back to academia? Like what were like some of the things that you were, whether they were people, things that you were doing, like what kind of helped you or along
I don't
that
know.
trajectory?
It's hard to say is anything. Let me
Like any
activate
like
the motion sensor. It's in a very weird angle block for my screen, so somehow the light is always
yeah.
darkened. Yeah, so I don't know. It's more like along the process, you just feel that okay, this probably is the time. And again, even though I did the research in the master program, but not necessarily I know very well. Okay, as you probably as a PhD student, you know that you start to have a glimpse of a small aspect, and then it's becoming more and more broadened in terms of perspective of what research is about and also other fields, right? So for me, is that I don't really know too much. Okay. So at that time when I applied for the PhD program, of course, I look at each school, but I don't really know like which specific fields I want to go into. But because of the research at that time, in fact, the 1999 is the Nobel Prize given to my former advisor, Ahmed Zewail, for the phenolchemistry time resolved study. And then in the year 2000, the Nobel Prize was given to the conducting point. Okay, so because of that, And also the research I did. So I of course read a lot of literature related to conducting polymer, but also have some like a time resolved pump probe kind of experiment. So I started saying, oh yeah, that seems to be an interesting thing, and I also started to feel that I probably don't want to do theory all the time. So I kind of made up an kind of decision to try go with experiments. Okay,
Yeah.
so that time the field is more like, yes, either the time resolve, that kind of thing. It seems cool, even though I don't know too much about it. And second is more like a nano science. Okay, and
Hmm.
the nanoparticles or the kind of thing was at the really the hot field in the late 90s and the early 2000s. So that's the kind of idea. So I look at the different schools and then the kind of research faculty doing these kind of research, like fields, and then I apply. Of course, I was kind of naive again. Along the way, I don't know much, so I just apply those kind of top schools. Okay, and look at which schools rank the highest. I would advise students don't do this. Okay,
Big
I
brain.
basically I just say, okay, these are the top like physical chemistry, not general, just physical chemistry specifically. Look at
Yeah.
their faculty research. Okay, these are seems to fit, so I just apply those are top six. Yeah, and then I didn't got half of the admission, so I would say I was bold enough and lucky.
Yeah, I was really because I know I mean I think your first year was like 2002 2003, and the late Ahmed Zewail won it in '99. So
Yeah,
it's very I mean that's right after he had won it. So
yeah. So like 3 years, 2022, 2023. Yeah.
yeah. Now before moving over to California, how was I mean leaving? Well, I guess you weren't really leaving your family for the first time because you had been to Italy, and I'm sure I don't know if you travel anywhere else, but
No, the International Olympiad is the country paid for
yeah, yeah,
the trip, and then
yeah,
that's my first overseas experience,
yeah.
and then yeah, and California probably the third. Yeah,
There you
experience.
go. I meant to ask this. I didn't. I had on Professor Taiyan Shen and Judy Wu, but
Mm.
I didn't ask them like good like Taiwanese food. Like I don't even know like in general, like I don't know if there's any like traditional dishes that like what's a
Oh
good
yeah,
traditional
okay.
Taiwanese, and also um are there any good like Taiwanese restaurants here in Houston? I don't know if you have any like I don't know if you know of any, and maybe
Oh,
in like Bel
sure,
Air.
sure, of course. Well, in fact, Taiwanese food, in fact, because of the history of Taiwan, we have all kinds of cultures that are mixed, and also, of course, we have the nationalists coming to Taiwan, and then
Yeah,
because they are people from all kinds of provinces in China, so they brought all kinds of their like, hometown dishes, and then they try to create the kind of the unique thing is kind of joining maybe different flavors or thing. So in a way, Taiwanese dishes, um, I don't know. There's a lot. Of course, there's also some kind of like kind of delicacies or
hmm. What
bistros
are,
or kind of food. Yeah,
what about like just like your favorites, like just like offhand, like some of your favorite dishes?
my favorite dishes. Um, I kind of like I like a lot stinky tofu.
Stinky tofu? Is that literally what it's
Yeah,
called?
right. I like it. So of course, a lot of the foreigners will be a little bit kind of feel not
What
feel
makes
that
it
this will
stinky? Like,
not appeal
is
to
it a
them.
sauce? Is it like a sauce or something? Like, I don't. Or is it just a funny name?
Basically what the flavor you feel when you eat it
Hmm.
and before you eating it, it could be very different. Yeah.
Interesting. Okay.
Yeah.
I'll
So
have to.
so some people is already repelled by that
Okay.
that smell, but actually eating it, they'll say actually it tastes good.
Yeah.
Well, there are also all kinds of other dishes, but a lot actually they have the significant overlap with, for example, like a Sichuan dishes,
Mm.
kind of Shanghai dishes, or like a Peking dishes. So basically in Taiwan you can find all kinds of food.
Okay, I'll have to keep
It
that in
really
mind
depends
then.
on which, and then some people they can eat like spicy. For me, for example, for my family, we can eat spicy, so we enjoy quite a bit of kind of Sichuan style.
Okay,
That style is a little bit too hot, yeah, too spicy.
I'll have to keep
But
that stuff in mind then, because I have to go check out some Taiwanese food. I don't even know if I've ever had specifically Taiwanese food.
yeah, of
So
course, we have those kind of like a night market, those kind of bistro type of food. Yeah, they it's quite so many, so it's hard to name any like, specific one as the thing I particularly like. Yeah, I
sure.
like pretty much a lot.
So anyway, you move over to CalTech. Any like first impressions when you first like got there? I mean, California, I'm sure, especially in CalTech. Is it? I think it is in Pasadena, right?
Yes, it's in Pasadena. Yeah.
I mean, I'm sure. Like, I mean, I'm sure there's no other. There's not many places that look like Pasadena. Just the beauty of the beautiful weather and
Yeah, that's
the beaches.
beautiful. Yeah, beautiful
Um,
weather.
so I mean, I don't know if culture shock's the right word, but were you like kind of shocked at that when you first got there?
Yeah, that's quite a bit, of course. Yeah.
And when you were there, how did you? I mean, did you know you wanted to join Professor Zewail when you first got there, or how did that how it
Um,
work?
yeah, I kind of know which group I want to join.
Mm-hmm.
Yeah, but the thing that challenged me the most in the beginning is actually the language. Okay,
Mm.
speaking, my English speaking was actually pretty poor, and also my listening also not very good. You know, those kind of you study from the book. You learn grammar, you learn word, but basically those kind of things that daily things you don't I did not have that much, so a lot of times actually I had to overcome things like you first formulate what you want to say and your mother language and then try to translate it in your brain
Yeah.
and then you get it out speaking. That's no, of course that's definitely is not the right way to learn a language, but unfortunately that's kind of thing I had, okay, at that time. So I was kind of had a little bit challenges in terms of kind of going up to a professor and talk because I
Mm-hmm.
was a little bit kind of can say hesitant and say, okay, what if I don't understand what he was saying? Well, what if I don't I couldn't really express what I want to say? So it's kind of things. So I only waited after I talked to other professors, okay, before I went to Ahmed Zewail, because I said, wow, he actually seems to be well respected. Time's precious. I don't know, and I don't want to screw up. Yeah, so,
Very thoughtful of you, for
I
sure.
waited about like a half a year to actually talk to him and then ask if I could join his group. Yeah.
Yeah, that's really. I mean, that's something that as a as an American living in America, and I never have to think about like my native language, right? But I can only imagine the pressure of like coming
Right,
over
right,
to a new country. You don't really know anyone, and you have to like you have to pick up the slang of a new language.
right, right.
You can learn a lot of stuff from the textbook, and maybe you're like on audio, you can listen to things, but it's when you get over here, it's the real deal, and um, especially like the science terminology and the jargon that sometimes gets tossed around. Like, there's not always a direct translation. I feel like, but that's so I do not envy that challenge at all. So
Yeah, actually, it was quite some challenge, some challenge. In fact, moving can say moving fast forward a little bit, skip ahead. Even it's still a challenge when I was joining his group and I
mm,
was given opportunity to do a seminar, a group seminar, and then I speak. Actually, it was hard for me, to really talk because you have to talk, a long time on your own, and also really kind of convey things as literature review kind of things. You have to put together things, and also in a good way, and
yeah.
you know, so that's actually a challenge. So in the beginning, I think I had a lot of because you're constantly thinking in your head and try to come up saying.
Hmm.
So basically, you process everything on the spot. Okay, so it was challenge, and I remember I used this word a lot, this filler word a lot. Basically, okay.
That was your filler word.
Basically, this is and basically
Yeah,
because
yeah.
I was practicing, right? Okay, so afterwards, Zewail, Professor Zewail, just pulled me aside and said, you said so many basically.
Yeah.
So I noticed that. Okay, and then later on, I had another chance. That's close to 1 year before my graduation dissertation defense. I had the opportunity to have this kind of campus-wide lectureship.
Mm-hmm.
That's more like a research award kind of thing, progress,
Mm-hmm.
and then you had the opportunity to speak to a general audience.
Right.
Okay, and
So
of course,
no more science jargon. Like, it has to be
yeah, you have
yeah.
to speak, and also and then now of course that was also a great challenge for me. So I remember after the presentation, and my as well came up to me and said, "Oh, good, you really do well." And I noticed there's no single basically in
Basically.
your talk. I said, "Oh, good, I
Yeah.
achieved something." Yes.
Yeah, you've come a long way then.
Yeah, right. That's a challenge.
I'm trying to learn German right now. Like, I have an app and try to learn German, but like something that's still like I hear what you're saying, like having to think in that language. Like, I have to think in English, translate it in German, and then speak it. So I can't like think in that second language yet. And that
Yeah.
is definitely a great challenge. And listen, you can only really learn a language until you speak it 24/7. Like, that's really the only way you can,
Yeah. So
you know.
in fact, I the thing one thing that helped me, everything actually all connected now, because I only started to become to learn how to really think in English and then speak like this, become more used to it. It's after I involved more in the some kind of the church events, and then
Mm,
the church event definitely I have a lot of time. You want to share your experiences, and also share what you understand from the faith, and then other things, and then from there actually. There's a one American friend I had even till today. So he was really patient with me. He's willing to listen to me for a long time, even though I was still formulating in my head, and then for hours, and then every week. And then only after like 10 or 11 times, I started to feel this thing, feel that, oh, there's something I start to grasp the understanding is what is thinking in English like.
mm.
Yeah, so
That's really
this is
awesome.
also kind of everything kind of help one another. So
Yeah,
that's
that's
kind of
really awesome. Are you still involved? I guess I could have touched on this earlier, but because you had mentioned, before your PhD, talking a lot about faith and the harmony between science and faith. Are you still like practicing? Are you still practice religion now? I don't know.
yeah, right, yeah,
What
still,
the
yeah, yeah.
okay. What religion do you practice?
Christianity.
Christianity. Okay. Any which I don't know. I'm so
Denomination.
yeah. I'm so bad.
Yeah.
I am so bad with religion.
Yeah, it's non-denominational, so
Okay.
it's okay. No
That's really
problem.
cool. Yeah. All right. That's really awesome. Um, I have. I think I received communion, but I never got confirmation. I kind of fell out with religion, but religion has a way of working its way back. If you're like, you got to be open to it for sure. I think.
Yeah.
So I hear that. But coming back to um, Professor Ahmed
Oh yeah,
Zewail,
right.
like,
Uh-huh.
wait, I guess somewhere where I think would be interesting is that he did win the Nobel Prize in '99 for his work in femtosecond, uh, studying reactions in femtoseconds, really. So
Right.
perhaps I kind of want to let you kind of explain maybe his work in that area and
Right.
the implication it has, let's say, on like the general, like what can be learned and what can be done because of this breakthrough of the time.
Well, yeah, in chemistry, it's more like trying to understand the at the molecular or atomic level how a reaction really takes place. Okay.
Mm,
And then of course, for more complex molecules, things are more complex. So he started from the simplest, the diatomic type of molecule, and then in gas phase, and try to understand what happens if you bring it to excited state. and then what is the reaction path. It could be some kind of relaxation, it could be a dissociation, and from there he discovered things that okay, sometimes we think okay, electrons is small, so it naturally have this wave particle duality. So you would think that okay, only the thing that are very small like electron or maybe hydrogen or proton might have a more like a quantum effect. Okay, and then they will think that once you get into like molecules or atoms, that kind of quantum wave particle duality is kind of diminished to a point that maybe it's not so prominent. Okay, but his study actually shows that you have to think about even for atoms, their movement. Okay, you should not think in the Newtonian picture. It's not atom A, atom B in a more deterministic, like a position, well-determined way of the reaction path. Actually, you also should think about the motions. It's like a wave packet. So that's actually was something revolutionary, or like people was a little bit kind of surprised by. Of course, later on, after we have more studies and people see all these kind of like quantum effect or wave packet kind of behavior, for the nuclear motions, they will see, oh, it seems natural now. But back then in the 80s, it's not so obvious. So he had the way to tell how a reaction really take place on their like a relevant time scales. Basically, like a tens or hundreds of femtosecond, and of course there are things afterwards. So he has all kinds of experiments. And then even when he started this study, he already think about other advancement. Okay, other the development of other techniques. So that becomes something that I involved in at a later time, using electrons instead of using laser pulses only. Yeah.
Okay. Yeah, it's really, I mean, this is like really fascinating stuff here. You touch on a little bit on like the idea of a wave packet. I'm not really in the quantum mechanical world, so I don't really understand. I don't really fully grasp like what that means.
Oh, right. Okay. So wave packet, because in quantum like mechanics or quantum chemistry, what we will learn is like this. If you because you have this Heisenberg's uncertainty principle, and you have this position and momentum, and in the same direction, linear direction, you cannot measure in infinite precision for both quantities. So you should naturally think about the nature, basically for all particles, no matter big or small, they always should use a wave, some kind of wave property embedded
Okay.
to describe its motion. Okay, so a natural way to think about is to consider a more like a distribution, and then when this distribution is so narrow, then you say, in terms of measuring the position, I have a well-defined position, because the width, which is a measure of what is the uncertainty in the momentum, or uncertainty of the position and also momentum, they have a finite uncertainty. So if you have a narrower width, which relates to maybe massier particle or motions, then it will be well-defined. Okay.
Okay.
But for lighter particles, especially for electrons or even protons, and then their natural distribution could be broad. Okay, so you use so-called wave packet that with a larger width uncertainty to describe its motion. Okay, and then in the femtochemistry, when you do the photo excitation, because of the setup of the experiment, you naturally promote the electronic state to the situation that nuclear motion is a combination of different, you can say, vibrational modes.
Okay.
And then those like a combination turn out to be like a wave packet. That's the best way to describe it.
Describe it.
And this wave packet, because different vibrational modes have different frequencies to move. So that means over time they will eventually broaden. So that means the uncertainty is no longer as well defined as initially prepared. So then broaden the uncertainty, and depending on how you probe it, you will have the opportunity to probe at different locations. That's become a distribution. So in a way, then using his way of chemistry to learn the reaction, he was able to find out this kind of wave behavior of the nuclear motions, and that becomes something that you can say provoke thoughts,
Mm-hmm.
and then that become a kind of standard language when we describe nuclear motion. We definitely have this wave property had to embed it. So not only just okay, motion's always Newtonian way of atomic motion with a discrete amount and a known amount, well-defined amount. Now we have to consider the possibility of like channeling between different normal modes, and then could be more like uncertainty, bound, or those kind of things together.
Okay. And these ideas, did this come out of, I mean, I don't really know how long this has been kind of thought about, but did this come out of the like Heisenberg uncertainty principle? Like, is this kind of how a lot of this work transpired, or is this some like completely different?
Uncertainty principle is that in the 1920, I think 1927. Yeah, so
Okay.
it's really early on. But of course, that at that time, later, we anticipate the uncertainty principle more applicable to small
Okay.
particles object, right? And then, but of course, in terms of theory, people already anticipate this thing. On the
Mm-hmm.
theory side, it's an experiment how to demonstrate this. Okay, or demonstrate is this true? Then Ahmed Zewail, he did the experiment to clearly showcase this.
Yeah. Okay. This is really cool stuff. Now, as a graduate student, I should also mention too. I think what's really interesting is that Professor Ahmed Zewail is that he's actually also the first Egyptian, I think, to win the Nobel Prize. So
Right,
he's the first naturally born.
So
So
he was revered as So in
yeah,
a way, in many aspects, he's like a pharaoh.
literally.
Like a pharaoh in many different ways. So he's like that, well revered in his home country,
Mm-hmm.
and also a lot in the scientific, of course, fields, and also in terms of the group dynamics, the way that we interact with him. It's kind of like that, okay?
Yeah.
Because he has so many projects going on, and then in fact his groups typically have more than 10, or even the largest could be like close to 20 postdocs.
Yeah. Wow.
No, not 20 postdocs, maybe more than 10 postdocs, and then a few graduate students. He
Yeah.
actually did not take that many grad students. He
Mm-hmm.
mostly have his postdocs. So each postdoc, of course, could have maybe 2 or 3 postdocs together on 1 or 2 projects. So how he operate this many member group, then basically we work, try to come up with as complete as possible the result analysis, even have some like theoretical models, kind of think about how to interpret it. And then when the time he finished travels, and then he arrived, he call you up, call maybe the subgroup up, and then you present. Okay, so it's like a grand review
Right.
in the kind of way, So he, in a way, you feel like you are presenting something to Pharaoh, like.
I'm sure.
Yeah.
I'm sure it definitely felt like that. But yeah, a little bit of trivia. He's a first Egyptian to win the, well, at least for STEM, anyways. I don't know about the other disciplines.
I think even
chemistry.
in the on the
Like
Arabic culture.
Yeah. Oh yeah. But so what did you work on as a graduate student? And I also want to ask too, like how, when you first met Professor Zewail, how did he describe the projects to you that you were going to work on? Like how, what made it seem really appealing?
In the first, because I came from the theoretical background, so I knew nothing. Okay, so in the beginning, he assigned me to a gas phase study and paired me up with a senior graduate student. So I learned first thing from the senior graduate student Han, and then and from there, of course, it's also a lot of things for me to take in,
Mm,
because you have all kinds of instruments. It's also a sophisticated instrument. You have the vacuum chambers. You have those kind of photo electron detection. You have those laser to intercept to a molecular beam. You have time of flight mass spec. So, and also all the electronics control, and also laser amplifier laser. So allow me for me to take in, but at least there's during the research in the beginning, we are doing this anion and electron detachment, and then try to study its dynamics, structure, like dynamics. I made some good contribution in a way to come up with a way to interpret it using a theoretical, it's a computational result to accompany and come up with a good result. So he was pretty happy with me in the initial assignment for the project, and then about like a year and a half into into joining his group, he asked me about a year. So he asked me on the side, what else in his group, what else research I would like to also do.
Mm.
But he already have in mind wanting to put me in the one of the newest group. Okay. But I said, oh, okay, I'm interested in that group because it seems it's kind of secretive. Okay. Not really release a lot of information in terms of what they are developing. I mean, yeah, interested in that. So he said, great. Actually, that's his idea. That also what he was thinking about. So he said, great. Okay, from now on, I moved you to another lab. So that actually is the technique I involved in the development. In fact, that's also the main technique I'm using here in the University of Houston. Okay, ultrafast electron diffraction. Okay, and then that I learned from a postdoc who, after 3 or 4 months, he started his faculty position in Michigan State University. So I was only have that packed time to learn whatever I could learn, and then starting my journey in that new. Yeah,
that's really cool. So yeah, as a graduate student there, what I know I know you mentioned you work on ultrafast dynamics now, but what so what was kind of that research or ultrafast electron diffraction? Is that what you were working on as a graduate student then?
yeah, I was
Okay.
a graduate student,
Yeah.
and then of course at that time it's more like a development of methods.
Yeah.
At the same time, look at the systems available to us. And now I'm doing what I'm doing here is to apply in the more specific directions and materials and also molecular thin films, and then to really push forward how we can really utilize it to visualize photo-induced changes.
Okay.
Because you typically in the time resolved thing, especially in the femtochemistry, the main thing used is laser pulses. So
Okay.
you have laser excitation. It's like this. How do we capture motions of molecules or materials at their very fast, their innate time scale, which is femtosecond. In fact, nowadays, electronic changes could happen at the attosecond, 10 to the minus 18 seconds. So it's very fast. There's no camera. Okay, yeah, there could be very specialized camera, but
there's no cameras. I can't
no
record it on my
camera.
iPhone.
The millisecond. Now the cell phone you have is just the millisecond. The better camera maybe a microsecond, but then all the things already done. Okay, so how can we capture that very fast motion? So if it's small molecule, then you can say I use laser pulses, and then use a spectroscopy to anticipate. Okay, this is the characteristic vibrational modes or something, and to kind of infer what's the structural changes. But if you have more complex situation, especially materials, you have a lot of atoms involved, then it becomes something by interpreting the spectral signature, whether intensity become bigger, smaller, or it's blue shift, red shift, actually will not tell you directly the structural changes.
Okay.
So if you use electrons, which have a much smaller, like a natural wavelength because of the wave particle duality, so you have the spatial resolution that by diffraction you are able to tell what is the spatial distance between, let's say, unit cells or molecular spacings. That small changes, now you have the resolution to resolve it. So the purpose to develop the ultrafast electron diffraction is for that purpose. Now, we could probably capture electronic changes, use optical pulses, but in terms of direct visualization of structural changes or lattice changes, then diffraction become a direct method and then that become hard to be probed by optical pulses. So
Okay.
in a way, that's kind of a strength and also the unique thing that diffraction, time result diffraction can offer. So the time result X-ray diffraction usually is offered in the large multi-user facility. You have to compete for the limited beam time. But electron, usually you can manipulate in the lab-based equipment. So that's how we kind of can build individual setup, and then you can do it locally instead of going to the national labs for the
Okay.
extra-based study. Yeah.
But actually, we can hop to that now because your research is. It seems like, at least the way I understand, it seems like it's a continuation, basically, of your graduate studies. What you worked on here now in Houston. But before we do that, actually, I wanted to ask you is, like, kind of at what point did you want to become a professor? And if you had any thoughts about moving into the, I don't know, industry jobs or anything like that. So how did that
Yeah,
all work?
that's also thing is yeah, I not sure that if I of course in Cal doing the faculty position is something I thought I hope I could do at that time. I thinking that's natural. You spend more time. I spent quite long years, 7 years with him as a student, and then another 3 years depending on the title, basically postdoc level. 3 years with him, so I have a decade. I have a
A
decade.
research experience.
Yeah, with him. So in a way, naturally, so you spend all the time in research, you have interest in it. So naturally, if I could also continue to really expand what I started it, then it'll be great. Okay,
Yeah.
but I understood the reality. Okay,
Mm.
so in fact, there's a reality check in a way. At CalTech, there was a one time there was a survey or kind of like a talk. Basically, it's more like maybe initiated by a postdoc association. Okay, so they try to survey. Okay, what kind of career path postdocs want to pursue, and then out of that, hundreds of postdoc, of course, about I think more than 60%. Okay, 60% want to be going into academia at the faculty position. All right, they are
That's
all
competitive.
very capable. In just one school, you have that many.
You're
Okay,
right.
then you count. You have so many top schools, and then all kinds of postdocs. So the number is huge.
Yeah.
So you well for yourself is that the chances. Okay, so in a way, yeah, I know the reality. So when I applied for the faculty position, I kept that in mind and said, well, I don't know. Let's see. So I applied the faculty positions. But there's one thing that's good for me is that because the techniques I was involved in developing, and also the postdoc I developed the scanning ultrafast electron microscopy. That basically I built the first in the world for that kind of setup.
Ooh.
So in a way, the technique I developed or helped develop is new, and then in a way, it's kind of highly sought after. So that kind of gave me some kind of edge. Uh, so I don't need to you can say a lot of effort try to make yourself distinguished. The
Yeah.
technique itself
Yeah.
have ability. Yeah.
A lot of your graduate work and postdoctoral research. I mean, it really just propelled you into progress you naturally into become your own, investigator, really, because you work on it now. So I definitely want to hop into it then. So the first thing is, yeah, like you just mentioned, so scanning ultrafast electron microscopy is one of the things you work on here in Houston, and you're able to get things like three-dimensional like images for material surfaces. And so perhaps maybe I guess we should hit the rewind button a little bit and how this came about, right? So what was kind of missing from the literature? Like what was kind of missing that you were able to develop this technique?
The you're talking about ultrafast electron diffraction or scanning ultrafast electron microscopy.
Scanning ultrafast
Oh,
electron
okay, okay.
microscopy.
Yeah, right. So in fact, that's the one thing, one major thing you can say the later part of Dr. Zewail's efforts in the development of a time resolved version of electron microscopy.
Okay.
So after you can say femtosecond femtochemistry. In fact, starting from 1992, he already started some version of a gas phase electron diffraction. But then it worked many years, and then after 2000, it started to have more effort going into the condensed matter phase for the electron diffraction. And then in 2005, he started having more effort on combining the temporal resolution with the transmission electron microscope. And then you have more effort on that. So naturally for me to think about, okay, when I want to do a postdoc, of course I could go away to do something else, maybe combining with X-ray based method, or maybe do some material based thing to kind of combine with my experiences and then come up with a program for myself to develop. But I thought about opportunity. Yeah, probably it's a good opportunity to develop the time resolved version of a scanning version of it, electron microscope. And then at that time, of course, to develop the technique, you had to be practical because any major development or method or technology, it definitely is heavy capital involved. So you have to have a new machine, laser system, everything. It's not a small price tag, but he has the resources and also this will become something I could contribute as a okay. I in CalTech to graduate, you have to formulate this a proposal, research proposal before the dissertation defense.
Yep.
So I have research proposals, and I wrote about this scanning ultrafast electron microscopy, and then I also detailed what could be used. Unlike the transmission, basically you try to image it. Scanning, basically the electron matter interaction a lot is inelastic scattering. Okay, and then eventually having the reduced kinetic energy of electrons. So all kinds of processes going on. So how we can make the temporal resolution, incorporate it, and then make use of this new information. So that's kind of the thing I discussed. And then he liked it. And then later on, I talked to him to stay. And then he said, oh, yeah, then we can make this project, basically realize it. And then, but still, he is not someone to say, all right, because he like it and it seems to work, and you just invest heavily directly. He still asked me to basically, he's sitting on his desk for a while. He had to work out all the details, tell him why it is definitely going to work, and then make my case. And eventually said, okay, yes. And then it's a big check to write out to purchase those equipment. Yeah.
How much was on that check? 10 million?
No, not that many. Okay.
Okay.
I think the total is
Big
probably about a million.
million? Okay.
The main part of the machine, because you have a really new S-UEM scanning electron microscope and also new fiber laser system amplified. So together, these two together is already, I think it's already 1 million.
Yeah. So I'm gonna be honest. Even I'm pretty unfamiliar with a lot of the instruments that you use. So scanning electron microscopy, like what is it? I don't think you probably don't get like spectra. I mean, you get images, right?
You could get spectra by looking at X-ray, or
Okay.
you could get it by, for example, the electron impact, the fluorescence, that kind of spectroscopy.
Okay.
But
I guess
usual imaging is no spectroscopy.
Okay. And something it's probably worth pointing out too is that we keep mentioning that's also like time resolved. So like, what does it mean to be like time resolved versus like non-time resolved?
Okay, so that's very good. So that touched the core concept that we are talking about related to time resolved studies. It's like this: how do we know the molecules or the materials behavior at a very fast time scale when they are doing it? So we said that the camera couldn't capture all these fast motions. So what we do is do so-called a pump pro method. So it's like actually like a running race. So a running race, everybody is all the athletes, all the runners started from the start line, and then you have the gunshot, and once you hear it, and everybody start moving, right? So the progress of this race, basically, you can say nowadays we use videos, but you can consider videos are actually accumulations of snapshots. Okay, so if you take a snapshot at 1 second, 2 second, 3 second, 4 second, you have a series of these, then you can trace the runners, the track, and then to figure out the progress, right? And then you can determine who's the winner. So it's like this. How do we know things are moving very fast? We want to take snapshots. So the way we take snapshot is that we try to use laser excitation to bring molecules and material away from the equilibrium. And now they are away from the equilibrium. They want to go back to the equilibrium state. So we try to monitor how they go back. And from that, it can give us some information about the intrinsic property of this molecule material. Because they could have different chemical compositions. They have different electronic structures. They could have a different, like a unique behavior. They are kind of buried. But when you try to bring them away from the equilibrium, electronic changes, they happen fast. Later, it's a nuclear motions. And then later, maybe thermalized the motion. So they now, instead of intertwine, like you couldn't distinguish by just a normal spectrometer or diffractometer. Now you use a time-resolved version of it. You bring them away from the equilibrium. They have their intrinsic time scale for their behavior. So that means you pull them apart. You can see, okay, now first electronic part, and then maybe the structural part, and then maybe the longer time scale for later things. So now you pull them apart. Now we try to use so-called a probe pulse. It's an interrogating pulse. It could be optical pulse. That means a spectroscopy, or you use electron diffraction, or use X-ray diffraction, or use X-ray spectrometer. So you can do all kinds of ways. The probe pulse can be different. And then once you have probe pulse, that's like interrogating the system. Ask, report to me what you're doing now. Okay. Tell me where your position is, or tell me where your state is, or tell me your configuration is. The interrogation pulse basically asks the system to report its current state. And you always have a fixed delay time between the pump and the probe. That means you acquire a snapshot at that delay time.
Okay.
And then you change the relative arrival time of these two pulses at the sample. Then you acquire another snapshot at different time. Then by changing the time for different time points, then you have a series of snapshots. Then you contain those kind of intrinsic dynamics or behavior of the samples you want to study. So in a way, if we don't talk about transmission electron microscope or scanning electron microscope, the time averaged version, so basically the normal operation, we call it time averaged version. Basically, you have the materials in the equilibrium. They could have their fast motion, but you have no way to resolve it. They're all mixed together. So you image under that condition. Now you use a laser excitation to force it to bring away from the equilibrium. They start doing their own thing. Depending on different systems, they have their unique behavior. It's like organic chemistry, like a mechanism. Okay. Have a different functional group. And that small different functional group can cause the mechanism to change. Why is that? Right. Because you have that specific behavior unique for that reaction. So this kind of time result study is that kind of like that. If I loosely use that analogy, we try to study how the materials are going back on their way to the equilibrium state and try to get the signature of their behavior. And from there, we take more about the systems. Yeah.
I guess something that's kind of it's not quite resonating with me still is like, I mean, it sounds like in principle that you can kind of study many things about whether it's a structure or let's say a material, but something that's still not really clicking with me is like the information that you're getting. Like, so let's just say we're in material science, you're studying a material. What I don't quite understand, like information you're getting from it? Like,
Okay.
that's
So let me, for example, use this recent study as example.
okay.
We recently studied so-called like a bismuth-based perovskite. Okay.
Okay.
In fact, it's you heard about the hybrid perovskite. That is a very hot material candidate for the solar cells,
Yeah.
right?
Yeah. Hmm.
So you have a lot of them basically is lead based. So you have a lead, and you have the halides, and then you have the structure like a perovskite structure, and then the cation could be cesium, it could be an organic cation, and people try to study how it can make it more efficient and also make it more robust without oxidation, without degradation, those kind of things. And then the key question for this kind of field is that it's interesting why the efficiency can be made quickly much higher, okay, improve much higher. And then it turns out that if we use time resolve method, we can try to understand how long the photo excitation generated electron and hole pairs they will persist in the material. Okay,
Okay.
so when we do time resolve experiment, if we don't have the temporal information, yeah, we may figure out different materials may have different efficiency, but why they are efficient, okay, then we can use time resolve information to tell us, okay, this material, somehow the photoexcitation allows the generation of carriers to be long-lived.
Mm.
Of course, the further questions are why would they be long-lived? And then you
Okay.
further do other design, do different compounds. Maybe the structure change instead of a three-dimensional network, make it a two-dimensional network, make it isolated like units, and see how these will change the dynamics or the generation of carriers, their lifetime. And then that time resolved information will be crucial for our understanding. We say, okay, when we have a more you can say inner look of their mechanism, then
Yeah.
we'll say, okay, let's apply it. Let's change a little bit of composition. Let's change a little bit of structure. And so for our study, we try to understand if we don't use lead-based perovskite, we use bismuth-based perovskite, which is
Hmm.
more environmentally or health like you can say friendly compared to lead.
Sure.
Okay. And but over the years, past 10 years, there's enough effort, but the efficiency could not be improved too much for bismuth-based perovskite. And then for this particular one, is an isolated bismuth 2 iodide 9 unit. And then we try to study its photo-induced behavior. So we found out that, and in the most recent paper, is that in fact the charge carriers, instead of being able to separate for electricity use, actually they form more localized.
Okay.
More localized, they don't want to go away. And because of that localization, it turns out to be quite long-lived. Okay, so it's quite unique. And also because of that, it affects the structure. So from our time resolved diffraction way, we can look at how the structure change over time. And from there to understand how carriers and the structure interact, then we make a proposition. We said that because of this behavior, we don't anticipate this material to be a good candidate for a solar cell material because it's hard to pull the carrier apart, even though the carrier seems to be long-lived.
Okay.
Instead, they might be able to use as more like a radiation detector, because radiation detector could be that you need to have a high energy particle, they will generate electron hole pair. You want this to be long-lived to have a way to be detected. So
Mm.
maybe this hybrid perovskite could have other functions or other use instead of a particular the target. Okay, for
Okay.
example, so that's the main target for a lot of research. Yeah.
Yeah, that
So
was really helpful. Yeah, that was really helpful. That definitely makes a lot more sense to me now. How that
yeah.
works then. How like robust are these instruments? Like, is it easy to just collect data, or like is it? I mean, I don't know.
It's
Like,
hard to put it to work,
okay.
but if it's well maintained or designed, for example, right now we could do experiment remotely. So actually, that's something is quite helpful in the pandemic. So
Yeah.
we automated in the sense. I don't know, after your podcast, this could be a target for the remote internet attack or something. I don't want to create
If you have actually, if you have any videos of like you using the instrument, like I'd be happy to like include that in like the bio or something like that. I don't know, like I mean, if you have a video something like this, maybe I definitely can include it for people to go watch how this
Oh,
works.
okay, okay.
I don't know if you have anything.
They
Yeah,
find it, no, or
yeah,
find how we can operate.
yeah,
So basically, is that physically if you load a sample or you want to change a valve or rotate something, of course you have to be physically in the lab.
yeah,
But
yeah.
once the sample is in the lab, those machines that have goniometers or can change the XYZ positioning angles, and then then you can raise the laser fluence like power, those kind of things by adjusting some kind of like optics directions, and there's like a motorized stages. They can
Okay,
do that. So then you can remotely log in and then do those adjustments and then let it go and see the preliminary result. It seems good. Let it go forward more to collect more data. So in a way, we have that kind of level of automation that seems to be helpful. Of course, we have to take care of the machine because it involves so many components. It involves a laser system, laser optics, vacuum system, and then vacuum system already have different parts. You have vacuum pumps, or those gauges, and also have an electron gun and also the electron detector, okay, which is amplified detection. So you have to have all things to work in sync for this to work. Yeah.
yeah. I remember we had new graduate students like come in a couple weeks ago, like as you know, and I had a couple of students saying uh, I like we like wandered back into the PCAM area, and man, the that first floor of Circ, the instruments you guys have there are really just, I mean, I've never seen anything like it. Obviously, coming from the organic, it was just really cool stuff that goes on back there. I definitely want to touch on the other areas of your research. So, uh, I guess okay. So you have the scanning ultrafast electron microscopy, which is imaging, but we also have the ultrafast electron diffraction. So perhaps maybe we should, what is the difference, right? And like maybe they're
So imaging basically is a real space. You look at it and you see as you understand. Okay, diffraction basically relies on the atoms or molecules. They diffract, they scatter off your beam electron, and then they will have this the you can say constructed interference to give you that diffraction spot intensity, and you analyze those kind of diffraction features. So in
okay.
a way, what we call it is a whole reciprocal space imaging. Okay, so it's not a direct imaging of each atom. It's not like a scanning probe, like imaging. You really utilize the interaction of a very sharp tip with an atoms or molecule to try to map the topography, or to try to have the, let's say, imaging of the surface condition, those kind of things. But we rely on diffraction to tell us together as atoms or molecules together, what is the structural manifestation in so-called reciprocal space. And
Okay.
then that basically is that's the same concept as the X-ray diffraction, for example.
Okay.
We don't look at the crystal structure. Okay, you don't look at the atoms or molecules themselves. You look at how they together, the repeated units together give you the diffraction, and then from there you try to backtrack what the structure should be, and then from there you try to tell the atomic or molecular structure or the or material structure. And then if we have a time resolved version of this, that means if we use external stimulus to make changes in like a transient changes, and then we try to capture those like fast motions, and then try to gain understanding from the changes to understand material behavior.
So similar to what we had discussed for the scanning ultrafast electron microscopy, would you be able to kind of give an example of like the applications of this and like maybe something that came out recently? I don't know if you guys published on this recently, but
Well, in
how's
fact,
it work?
the work I described to you, this Prof guy,
Yeah, was it
with
both?
metal, that actually is from diffraction.
Okay.
If it's for imaging, then another work for example, try to understand this boron arsenide.
Hmm.
Boron arsenide, this is a semiconducting material, and also have a second to diamond, the highest thermal conductivity. So you
Oh
want
wow.
to understand, okay, once you have photoexcitation, now you create electron hole. You create hole in the valence band, electron in the conduction band. How their no, what is their mobility? Okay, how they can diffuse or keep separated, and then maybe the dissipation of them. So we used with my collaboration with a friend in UC Santa Barbara, and then we try to image directly look at how the carriers diffuse away from the center of the excitation. So,
Now,
so
in,
that is the real space. And then for a lot of my studies involving diffraction, then let's use a reciprocal space diffraction.
mm. In your group now, do you have like, let's say, independent projects, or do you like collaborators around the world like kind of come to you and like, hey, look, we have this material, can you study this, or we want to run this, like, or do you have like your own individual studies?
Oh yeah,
You gotta.
we have both. We have both.
Okay.
We have
Okay.
the individual studies that, especially related to molecular thin films.
Hmm.
That's what we can make in the lab, and also to examine different interaction. Let's say hydrogen bond or dipole-dipole interaction or van der Waals interaction, or how they affect the molecules to assembly themselves.
Okay.
Then and look at how laser excitation cause changes and try to understand energy transport across interface, or depending on the structure, how they have impact on that. So
So
that
do you
that's
have to
how
synthesize those ultra films then, or like do you like?
the film basically is using a like vapor deposition to kind of
Okay.
format. For the things that, for example, like a 2D materials or the perovskite kind of studies, yeah, we try to collaborate with others because we don't make the materials
Hmm.
themselves. We have a collaboration. So then there's actually the perovskite study actually was initiated like a from inquiry from a researcher in India, and then asked me if I could do research about their materials. So
That's
in
really
a
cool.
way, yes, now there's also some collaboration.
So there's opportunities for collaboration
Yeah, sure.
within
In
your
fact,
group.
I always talk to our incoming students. I welcome the opportunity that you have a joint research program. Of course, you have to see the capability, but a lot of
Right.
times, for example, especially inorganic, like solid state materials, then this become actually more relevant because we could have, let's say, join the project. It's a synthesis, and then you have a characterization using a advanced tool, and then to have a deeper understanding. So then the collaboration definitely is something we want to keep doing.
Yeah, it's really fascinating stuff. As we begin to wrap up here, I guess one of the last things I wanted to ask you is, uh, what are like some of the outstanding problems like within the field of, let's say, like what are like areas of improvement for, let's say, ultrafast electron diffraction and microscopy, if any, like where are people trying to still improve?
In fact, this field, like the ultrafast electron diffraction, or the complementary one, or you can say even say the competing one, is the ultrafast like X-ray based
Okay.
technique. Okay, they can also do diffraction. They can also do imaging. They can also do spectroscopy. So in a way, there's a lot of actually nowadays become more after the last 10 or 20 years. It become more available.
Hmm.
So it become more accessible in a sense that it can be applied to various different systems. Okay, but in terms of technique wise itself, of course, I'm not really developing it, but I know the field that they try to first, for example, try especially for electron pulses, how to make electron pulses even shorter in time.
Mm.
Okay, because electrons not like photons, they have repulsion. Okay.
Yeah.
So you have Coulombic and repulsion. So if they travel longer distance, they start to affect each other, repel, and then naturally you broaden the, the spatial and those temporal width, and which will be not so good. They have multiple strategies try to do that, but this kind of different fields like going from here, they have to use maybe some kind of quantum control. They try to maybe do some like compression techniques. They even try to use high harmonics, try to try to approach attosecond, basically sub-femtosecond kind of pulses. So that's still very challenging. Okay.
Mm.
In fact, it will be also very difficult for me to implement that kind of compression in the current lab I have. So that kind of is quite specialized, advanced. But of course, when you have an advanced tool, usually the information obtained is quite rare and they're also important, impactful, and they tend to be appearing in high impact journals. That's kind of tend to be like this way.
Yeah.
And then in terms of microscopy, of course, there's all kinds of things that try to see maybe combining really temporal resolution, also at the same time the spatial resolution really to angstrom or even sub-angstrom resolution. There's still challenges in these areas.
Yeah.
So we want to have a simultaneous spatial and a temporal to really capture atomic, molecular, or materials responses at very fast time. Yeah.
Well, this is a extremely exciting area of research, and like I said at the beginning, I really didn't even know what you did here in Houston, so I was really glad I got to talk to you today. It was extremely fun. I had a really fun episode. I want to thank you for your time on the show today, and so I look forward to seeing what comes out of your lab.
Thank you,
and
thank you for the opportunity.
Yeah, and if you're interested in ultrafast electron microscopy and diffraction, be sure to take a look at Professor Jerry Yang here in Houston, and for any prospective graduate students, check it out. But alrighty, I'd like to thank you for another episode, and then we'll see you in the next one.
Yeah, thank you.